Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo.
All right, so for you guys that were on last time, welcome back. And for the guys that are signing in for the first time, thank you for joining us. The idea of these sessions is we're trying to basically do a meter school between last week and early December. We're trying to do a 1-hour session every Tuesday, and we're aiming it for kind of the intermediate to advanced metering folks, as well as also handling some current topics for folks that are a little bit more experienced. So we think it should be interesting for everybody. We're hoping so. If you find it useful, tell us. If you didn't like us, don't tell us. No, if you didn't like it or you thought it could be better, please let us know. That way we can make it better the next time. We've got a whole series of them, and there's a schedule I'll show you at the end. You've probably seen some of the emails of them. So with that, we'll get going. Today we're going to be talking about transformer-rated and self-contained metering fundamentals. Again, the idea was we're aiming for the intermediate and advanced. So we're going to cover a little bit about self-contained metering and a lot more about transformer-rated metering and the importance of getting out there and doing it, and some of the technical aspects of it, as well as why. All right. So topics we're going to be covering: the basic differences between self-contained and transformer-rated metering sites. Some of the different forms. We're not going to dwell a whole lot on that, other than to talk about the fact that there are a bunch. Test switches and CTs, Blondell's theorem and why it matters to us, so you're not going to get away from some of the math at least. Meter accuracy testing in the field, checking the health of your CTs and CTs, and site verification. It's not just meter testing or transformer testing. It's also about checking the entire site. Okay? So we'll start with the basics. Self-contained metering. Why is it important? Well, it's what most of our metering is. A little over 85% of most of our meters are 2S residential self-contained. There's other self-contained forms, Form 12 and 16 and a couple of others. These are typically found residential metering, maybe some very small commercial industrial. The meters are sized and are capable of handling all of the incoming current. Which means what? It means that the meter is part of the circuit. If you take the meter out of the house, off the building, it kills the service. Now, if you use horn bypass jumpers, you don't have to kill the service, but basically you would have to jumper around it because the meter is part of the circuit, all right? And it is connected directly to the load being measured. Most of our class meters are class 200, meaning that they can handle 200 amps. There are class 320s, which can handle 320 amps. Okay, that's your basic self-contained metering. All right, the meters through the years, basically they were induction meters. Everybody's familiar with the electromechanical meters. Even though we haven't been making them for almost 20 years, there's a ton of them around. We are a very conservative industry. The major meter manufacturers have been making meters since the 1890s, and I'm talking about GE, which became Aclara, which became GE, which is Aclara. You've got Westinghouse, which became ABB, which became Elster, which became Honeywell. Those two guys were making meters in the 1890s. Sangamo, which became Schlumberger, which became Itron. They were making meters in the 1890s. And Duncan, which became Landis & Gyr, which became Landis Plus Gyr. They were making meters in the 1890s. All those guys came up with induction meters in the 1890s. For a little while, there was a patent infringement from like 1903 to 1910 where two of them couldn't make it, but then they got right back into it as soon as the patent was over. Census is a little bit newer player, but not really. They have a long history in the gas and the water market and then jumped into the electric. So our manufacturers have been around for a very long time. The basic induction meter has been around for a very long time. All right, let's go and do just a little bit of the basics. Ohm's law, V equal IR, probably the most useful, the most fundamental of it, and from there, everything else goes. All right, Most of you guys, if you took any kind of electrical engineering or any kind of tech school stuff, people love to compare electricity to water flowing from a hose. I'm not going to spend a whole lot of time on it, but just real quick, the voltage is equivalent to the pressure. The current is effectively the rate of the water flowing through the hose, all right? The impedance is the resistance, and the power is how fast the water flows from the pipe, gallons per minute versus kilowatts, okay? So you got these two setups. One of them effectively has an amp, one of them effectively has a volt, and it's got a resistance of 1 ohm. This one has greater resistance, so the pipe is narrower. It's only got a half amp, it's got 1 volt. They're both equivalent. V equals IR, okay? The pressure coming out of here is a little bit more than that one. Okay, and basically you got a battery, you got a pump. You got flow, you got current, you got flow rate, you got volts. And you can see 50 pounds per square inch, nothing, 12 volts, nothing. You got your resistor and you got your constriction. All right? F equal delta P over R, I equal delta V over R, Ohm's law. All right? Just a couple of real quick ones. When I do this at a meter school, I usually get the students a couple of seconds. 20 volts, 5 amps, what's the resistance? V equals IR, it's 4 ohms. All right? R is equal to 20 ohms, V equals 120 volts, V equal IR, it's 6 amps. I equals 10 amps, R equals 24 ohms, V equals IR, 240 volts. All right? So we just kind of go through real quickly. It's pretty easy to calculate. It is so basic, and yet it is so fundamental to everything that we do. Why? Well, what's power? Power is VA, voltage times current. Okay, that's what it is. You've heard a little bit about it. Right now, as we're giving this presentation, there's a series of ANSI meetings that are going on. We hold them twice a year. And one of the working groups that was earlier this morning is the VA working group. And the concept there is, can you maybe just do your metering just on VA and not worry about phase shift? And we'll talk a little bit about that in a few minutes. Okay? So power equals voltage times current. And again, I go through a couple of quick examples when I'm usually doing an in-person meter school. 20 volts, 8 amps, what's the power? 160 watts. 5 ohms, 120 volts, what's the power? 2,880 watts. 10 amps, 20 ohms, what's the power? I squared R, it's 2,000 watts. Okay? Of course, we don't usually work in watts. We're usually working in kilowatts. So that's 2 kilowatts. And then, of course, if you're getting more into your generating or your renewables or something, it's megawatts, right, which would basically be 1,000,000 watts. All right? Now, fundamental. One of the really important things in our industry is active power and apparent power. Your power factor is nothing more than the ratio of those two. Active power divided by apparent power. What the heck is the difference? We bill our customers based on active power. What we deliver to our customers is apparent power. So if your power factor is 1, what you are delivering and what you're getting paid for are exactly the same. As your power factor starts moving away from 1, you start delivering a lot more power than you are actually getting paid for. Most utilities have especially for your C&I customers, most utilities have some sort of penalty to industrial customers who have a power factor that falls typically below 0.9, and then you charge them a correction fee of some sort, and everybody's just a little bit different because you're delivering a whole lot more energy than you're getting paid for. All right? So VA is equal to E times R. Power factor is just, again, your active divided by your apparent. All right? If you go out and you ever see a phase diagram, you can see your current and your voltage laying on top of each other. That's perfect. That's exactly what you always would love to see. That's a power factor of 1. All right? So again, 120 volts, 60 amps. How much is being drawn? 7.2 kilowatts, or 7,200 watts. All right. How many VA? It's exactly the same because your power factor is the same. All right. Power is also sometimes called demand. All right. The actual power is E times I times the power factor. So VA times the power factor. All right. No harmonics are there. Nice sinusoidal. Everything lays right on top of each other. Everything works perfectly. All right. And you can see this is the idealized situation. Everything working perfectly. However, it doesn't always work perfectly. If I have a power factor of 0.866, and you can see right here, current is not laying right on top of the voltage. All right. All right. I'm not being paid for all of the energy I am delivering. I'm only being paid for 86.6% of it. Okay. And this one's even a little bit worse. I'm only getting paid for about 71% of it. All right. Now, yeah, kilowatts. Again, only getting paid. I don't have a very good power factor here. All right. Now, we actually get paid for energy, which is a kilowatt hour. Same thing with your bucket. If you had 5 gallons per minute, you want to know how many gallons I actually got. If you're selling me gasoline, you want to know, okay, great, I'm pumping it at 5 gallons a minute. How long were you actually at the pump so I can tell how many gallons you actually got? Same thing, it's a kilowatt hour. Okay? If anybody has any questions, feel free to put them in the chat. I know a couple of people are have been putting a couple of notes about connection and stuff. But if you got any questions, just throw it in the chat, and we'll try and stop and answer any questions. I am trying to go relatively quickly through some of the introduction stuff because I don't want to bore the folks that know it really well, but I'm also trying not to lose the folks that aren't quite as familiar with it. Okay? All right, 120 volts, 45 amps, power factor of 0.9 for a day. That's 24 hours. How much energy are we using? 116 kilowatt hours. All right. Again, if I've got a power factor of 1, how much am I using? 79.2 kilowatt hours. All right. Now, here's a more practical situation where I'm drawing it during the day when the plant's going. I've got a horrible power factor of 0.8, and I'm drawing most of my power then, and it's from 8 to 6 that I'm doing this. That's the average that I'm pulling. At night, I'm using a lot less, but my power factor jumps up to 1. Okay, that's a fairly typical scenario. So how much energy is being used? I got 10 hours in the morning, 14 hours that I'm shut down, and I'm using 19.2 in the morning and 1.68 through the evening hours. So even though I've got a nice power factor, I'm not actually drawing that much energy because it's the evening, my plant's closed. All right, and total for the day, I drew 20.88 kilowatt hours, or I paid for 20.88 kilowatt hours. You actually delivered more because my power factor during the day is kind of miserable. All right, so let's go back to our electromechanical meters and our discs. Everybody's probably heard of K sub H. It was a very clever invention. They recognized the induction meters when they developed them back in the 1890s. They realized that the amount of energy being consumed was directly proportional to the disk spin, or something that would spin. So they developed a meter that had a disk. They tried to make that a frictionless bearing, or as close to it as they could, between magnets and jewel ball bearings. They made that disk as frictionless as possible, and the K sub H was the number of watt hours per disk revolution. And that's really clever because now all you have to do is count disk revolutions, and now you can basically bill the customer on watt hours. The very first meters, going back to the 1870s even, had little clock dials because the very first ones were no more than clocks. They simply measured the amount of time that the electricity was on, and back in the very earliest days, there were no switches on the circuits, and there was a constant draw from the bulbs that were on the service. So if you simply counted how long it was on, you could give them a meter, you could give them a bill. Well, those clock dials never went away. They stayed with the electromechanical meter through the early 2000s. And again, very clever, Every disk revolution, you count the number of disk revolutions, you know how many watt hours. We never got away from that with pulses. Between every pulse, for every pulse, it is a certain number of watt hours per pulse. Count the pulses, you can give a meter. So we're doing the same thing now with our electronic meters. You simply put in your pickup or your probe, your combination pickup and probe, and you can do a meter test because you just count the pulses and you know exactly how much energy is being drawn. Okay? Meter accuracy testing. When you're out in the field and you're testing your meters, when you're out in the field and testing your meters, you're basically typically you're doing 3 tests: a full load, a light load, and a power factor. And whether you're doing that in the field or you're doing it in your shop, those are your standard 3 tests. Okay? Now, let's jump into real quick transformer-rated metering and how that differs before we get too far into testing. So the meters in a transformer-rated service typically cannot possibly handle the amount of current that is coming into the facility. This is usually your commercial and your industrial facilities. You're bringing a lot more power than the meter can possibly handle. So what we did, going again all the way back to the 1890s, is we scaled the meter. The meter is basically just a scaled down representation of the load. So if you've got CTs in there that are 400 to 5, that means for every 400 amps coming into the building, the meter only has to see 5. Okay. Sometimes you also do that on the voltage, and you have PTs in there as well. The key here is the meter is not part of the circuit, because we certainly don't want to go out to a very large customer site and when we pull the meter, interrupt their service. You can't do that. Typically, your commercial industrial sites, as meter techs, the one thing we can't do, unless there is a scheduled shutdown, which sometimes takes an act of God from with some of our customers, you can't ever shut it down. So the meter is not part of the circuit. You use your test switch, you bypass the meter circuit, and now you can remove the meter, you can clean up the socket, you could replace the socket, you could test the meter, you can test the transformers, you can do anything that you want to do there. All right? So that's the very basics of transformer-rated metering. Okay? What do I have? Well, I've got these three CTs here. Okay? These are instrument transformers. That means that they are precision transformers. And they do need to be tested, and they have to have a certain accuracy class to be considered instrument transformers. They've got to be at least 0.3 up through some burden. And when they say 400, it's actually implied that it is 400 to 5. And for those of you guys that were on the call last week, the reason that we go 400 to 5 is because the very first polyphase meter that was designed by Westinghouse in like 1898 was a dual stator meter, and it was most accurate at 5 amps. And so all of the instrument transformers were made to go to 5 amps, and we never got away from that practice. Do we need to do it today? We don't need to do it today, but we've just always done it that way, and that's the way we do it. Because once upon a time, those polyphase meters, their sweet spot was 5 amps. When you test polyphase meters, typically full load is still 5 amps. That's what's considered full load. So you typically have your 3 transformers on phase A, phase B, phase C. They are connected through a test switch to your meter. Okay, so if you looked up at the up here, you got your test switch and you got your socket. Sometimes if you put the CTs in the same cabinet, that's called a trans socket. More typically, the CTs are in a separate cabinet, usually fairly close. You want them ideally as close as possible to the meter and the test switch cabinet. Okay? All right. Also, if you look at it, you see this little white dot up here? That gives you your orientation. So you make sure that these CTs are all oriented in the same direction. All right, we'll talk a little bit more about what happens if you didn't do that. All right. This is your traditional, this is not an extended range transformer. This is your traditional instrument current instrument transformer. All right. So in this particular case, it's 0.3% accuracy class, so it makes it an instrument transformer, and it usually tells you up to what burden it's good at, a burden of 1, a burden of 0.5, and we'll talk a little bit more about that in a few coming slides. And then you have a rating factor. It's really called a thermal rating factor, but we shorten it to rating factor. And in this case, it's 4.0, and that's fairly standard. This is a pretty plain vanilla instrument transformer, okay? And I stole this particular one from GE. But again, there's several manufacturers. They're all very good at what they do. So 0.3, you would think that if it's a 400 to 5, and you were to put, say, 200 amps through it, you would think that you should get 0.3% accuracy, and you'd be wrong. Because it's a 400 to 5, that thermal rating factor means that you could actually go with a thermal rating factor of 4.0 on a 400 to 5 CT. You could go up to 1,600 amps. You could put through it, and as long as you don't exceed your burden, you should get 0.3% accuracy. Okay? You don't want to exceed it because it's a thermal rating factor. You exceed 400%, and you're going to start doing bad things to the windings in that transformer. You're going to start breaking down some of the insulation. You're going to damage your transformer. As long as you stay below 400%, it's going to maintain its accuracy very flatly. It's amazing when you test them. It is amazing how accurate they remain. Once you go down to the rated number, 400 in this case, because it's a 400 to 5, your accuracy, it doesn't jump up as a step. It actually kind of does more like this, but for idealized purposes, what you'll typically see is a step function. It actually doubles to 0.6%. If you read the faceplate of that transformer, do you know where you will see that information? And the answer is nowhere. You will never see it. It doesn't show up. You're just supposed to know it. You're supposed to know that below 100%, its accuracy goes in half, meaning it goes from 0.3 to 0.6%. So in a perfect world, if you think that you're going to typically have 200 to 300 amps on a particular customer's service, and yes, he may go up quite a bit at times when he's turning things on or something, and he may go down at times when there's nothing going on, you don't size a 200 to 300 amp load with a 400 to 5 with a thermal rating factor of 4. You really want to size that as maybe 100 or a 200 to 5 with a thermal rating factor of 4. That would be a lot better for that size because your accuracy in here is actually less. The other thing that many people don't recognize is if you oversize your CT, not only does your accuracy go in half, and you may always be measuring at 0.6. So let's say that 200 to 300 amps, you would actually put 400 to 5s on. You're always going to be measuring at 0.6. And when you go down to 10%, there is no rating. You may not be getting anything. You may not be getting any measurement at all, or if you do, its accuracy is going way, way down. So you're effectively getting no meaningful billing data, which means if I put a 400 to 5, 10% of that is 40 amps. Well, if I've got a customer only drawing 200 to 300 amps typically, at night with just the lights on and a few computers and stuff, he may only be drawing 10 or 20 amps. So basically I'm giving away all the power in the evenings. Okay? Now your extended range transformers are better, and the extended range transformers will come down. Some of them claim to be doing better than 1% at the low end, and they talk about maintaining their accuracy throughout their range, and extended range is exactly what it seems. It even has a larger range. Okay? All right, hold on a second. Got a question. What happens with CT if you go above 400% or above the rating factor? So again, if you go above the rating factor, it's a thermal rating factor. You start to heat up the wire. As you heat up the wire, that copper wire, which is typically copper, not always, but it's typically copper, starts to expand. As it starts to expand, it's encased in insulation. If you heat it up too much, what's going to happen is it is eventually going to break down that insulation. As soon as it starts to break down the insulation, now you can get shorts between the windings, and your transformer basically is no longer going to function correctly for you. Because if you short between the windings, now you have a different number of windings. And a 400 to 5 CT is pretty simple. It's got 400 windings on one side and 5 windings on the other, or it's got 80 on one and 1 on the other. it's got that ratio of 400 to 5 in it, and that ratio is simply the number of windings. So if you exceed the thermal rating factor, what you do is you heat that wire up and you can start to break down. Because it expands, the only thing you can do is put it's going to try and expand, it's going to put a lot of force on that insulation, and eventually it's going to crack and break it and can short out. All right, so hopefully if that answered the question, just type a yes in there. If it didn't, just keep asking, Matthew. All right, okay, so current transformers and voltage transformer testing is pretty simple. Of course, I'm putting a shameless plug in for our equipment, but this is a CT testing system. This is a VT testing system. These systems here are designed for, these are obviously not field equipment, this particular equipment. This is shop equipment. They're very high precision pieces of equipment for determining, doing a lot of type testing and acceptance testing on your transformers. But they both operate in the same fashion, the same way any kind of meter testing works as well. You have a precision transformer right here. This is on the voltage side. And you got a loading transformer right here. Inside of this cabinet, you got the same thing. You got a precision transformer that basically operates. You have a precision and a loading transformer. You can pair the transformer under test, which in this case on the current side is hooked up over here, and on the voltage side is connected via cables to the loading transformer. And you compare, what did the system, in this case here or here, what did the system send through the loading transformer to the precision transformer and the transformer under test, and you compare them. It's pretty basic. Whatever you saw here, you compare that to what you saw at the instrument under test. You consider this to be perfect because it's a precision transformer, and however much different the instrument under test is, that's your accuracy. If on the current side, if you only saw 99.2% of what the precision transformer saw, that's how accurate you would be. And the instrument transformers, by the by, are usually much more accurate than that. Same thing with the voltage transformers. So again, pretty simple. Loading transformer, loading transformer and precision transformer, and transformer under test. Okay. Current transformers. Do they typically, if they're going to, are they ever fast or are they ever slow? Meters could be fast. Typically, they're a little bit on the slow side. Meters are. The reason for that is meter manufacturers, with one exception, one time, always calibrate up to 100%, which means that typically when you get the meter, it's 99.9 something. It's very close to 100%, but it is not typically over 100%. I'm not saying it can never be, but if you take 10,000 brand new meters, the overwhelming majority of them are going to be just a hair under 100%. Not so with instrument transformers. Why is that? Because of the basic design. Remember I was telling you about the ratios. This is the ratio. You got coming in, I got 1 turn. Coming out, I have 10 turns, let's say. Let's assume that was 10. That would mean I would have a 50 to 5 transformer. That's what it would be. 10 turns to 1 turn is the same as 50 turns to 5 turns. Why do we go to 5? Again, because back in the 1890s, that was the sweet spot for our polyphase meters or for our transformer-rated meters. However, a transformer requires a certain amount of energy to actually function, all right? And that's called an exciting current. So I have to have just a tiny amount of energy to go through, a tiny amount of current to go through and get that transformer working. Well, that tiny amount of energy is lost on the primary side, which means that when I come off on my secondaries, I'm always going to be just a little under 100%. So anybody that tells you, oh, I got a transformer that's registering over 100%, there's something wrong, okay? Your transformers are always going to be under 100%. They're always 99.99 something because by design, they require an exciting impedance. So again, it's an important fundamental about transformers. They're always less than 100%. All right? Now, what are we primarily interested in checking on an instrument transformer? We've got them all over the field. What are some of the things that we want? Well, one of the things that we want to do is we want to check the burden. Why do we want to check the burden? because that nameplate that you can't quite read over here tells me that it's 0.3, but only up to a certain burden, okay? If I exceed that burden, my accuracy goes down, all right? And you can see over here, this is that nameplate that you couldn't quite read. And again, several transformer manufacturers, they're all very good. One thing about our industry is anybody that supplies equipment into our industry, they make good stuff. And the reason is our utilities do not accept anything but the best. You guys expect that when you're buying something, it's good stuff. And if you've got a vendor that doesn't deliver that, they're not going to be in our industry for very long. So unfortunately, even our competitors deliver good stuff. Now, they all do. Everybody in the industry makes good stuff. This is an Alstom transformer here, and it tells you right on the faceplate, 0.3% at a burden of 0.1, 0.2, 0.5. So up to half an ohm, this is going to maintain its accuracy. What happens after that? After that, so here it is, 2 ohms, 1 ohm, half an ohm. It's very good, okay? It's supposed to be a something to 5, and I'm getting 5 amps out of it. In fact, I'm actually getting 5 amps as I pass 1 ohm. As I get 2 ohms, I'm just a little bit less. You can see 4.99, 4.98 at 1 ohm, 4.95 at 2 ohms. So I've lost a little bit of accuracy, haven't I? Lost about 1% of accuracy here. But as you get an increasing amount of burden on there, my accuracy goes way off to the point where it's kind of useless, all right? So you really want to keep this particular setup at less than half an ohm of burden. Well, how do we get burden in a setup? We're going to talk about that, and that's part of site verification. But you can get it from loose connections. You can get it from corrosion. You can get it from setting the CTs too far away from the meter. We talked about ideally wanting to keep them as close as possible. The amount, you've probably heard, sometimes for whatever reason you cannot keep the CTs close to the meter. Sometimes there are logistical reasons why you just can't do it. Well, as soon as you exceed a certain distance, you probably all have seen where you have certain guidelines that say, oh, you're going to go further than 5 feet away. Well, now you have to increase the size of the wire. Why are you increasing the size of the wire? You're increasing the size of the wire to reduce the resistance in that wire, reduce the burden. And you got to reduce the burden because on that faceplate it says, hey guys, you can't go more than here, otherwise we're going to start losing accuracy. So one thing that you check when you go out to a site, you take ours or anybody else's burden tester and you do a burden check on your CTs, okay? It's a nice, important test. Typically we've got red, yellow, green. It's pretty self-explanatory. If it's in the red, you got a problem, all right? And if you got a problem, you do want to address it because those CTs are giving you they may be giving you very inaccurate readings now, okay? As you can tell, it quickly drops off, all right? What's the other thing that you want to check? The other thing you want to check is the ratio. Why do you want to check the ratio? You want to check the ratio because if you have an incorrect ratio out there, if I tell you that I've got a 400 to 5 transformer, but really I have an 800 to 5 transformer out there in my service, that means I'm only going to be giving half of the bill. I'm going to be losing 50% of the revenue, all right? The ratio, it's pretty simple to do. You can use a piece of, equipment like ours or any of our competitors, or you can just get a little, if you have access, you can get some ammeters. And you're simply checking the primary versus the secondary. And you can do that you have to access the primary and you can check the secondary right from your test switch, and you can calculate your ratio. Now, one of the things, I don't know if you noticed or not, but on this faceplate, okay, there were 2 different ways in which you could hook this particular transformer up. X1 to X3, X2 to X3. Depending on how I hook it up, I have, in this particular one, it was a 300 to 5 or 150 to 5. These are called dual ratio transformers. They were very popular in the 90s and 2000s. These came out before extended range transformers came out. And they allowed utilities to reduce their inventory because now you could have one transformer that covered a larger range of ratios, and the rating factor was 1.5. It was 1.5 for both of them. So theoretically, I could go from 150 amps up to about 450 amps with this particular transformer. The problem is anybody that has dual ratio transformers out in the field in any numbers, more than a few dozen, I will guarantee you that somewhere on your system there is a transformer that you think you wired one way, and it's actually wired the other way. And when I say you, I mean the billing system. So the billing system is set up one way, and you've actually wired it the second way. It may be that you're sending the customer half of the bill, or it may be that you're sending the customer twice the bill. All right? So when you go out there, what you're checking for is the ratio. Are you looking for a highly precise number? No. You just want to make sure that it's roughly 400 to 5. So if I go out there and I'm reading 80 amps, I want to make sure that I'm getting about 1 amp on the secondary, roughly. I could be off by 5 or 10% because we didn't make a 390 amp to 5 CT. We made 100 to 5s, 150 to 5s, 200 to 5s, 300 to 5s, 400 to 5s. They're fairly widespread. So you just need to get in the ballpark. All right? Meter forms. There are a lot of meter forms, and they are constantly adding more. At some of our ANSI meetings, there are actually petitions within the last couple of years for new and different meter forms. Most utilities probably don't use more than 20 meter forms. Some use less than that. Many use less than that. But there are many different meter forms used for a variety of different reasons, for a variety of different services. So depending on the service and what you're trying to do, you may have a very good reason. You typically do have a very good reason as to why you would pick a particular form. There are lots of different ways to skin the cat. You can appropriately meter a single installation with a whole wide variety of different meter forms if you wanted to. A lot of it goes back to what does your utility like to do? What does it typically do? All right? So in talking and introducing forms, I'm going to jump back to Mr. Blondell. All right? So this is a picture of Mr. Blondell back in the 1890s, and if you notice, he's a pretty young guy. Well, that's because in the 1890s, they basically invented this industry. And they were, other than maybe Edison, they were all pretty young guys because it was all brand new. The first crop of what would later become electrical engineers were graduating from universities. The U.S. Navy and most of the navies around the world was a huge pioneer in electricity because they saw the ability, just like many decades later, the U.S. Navy got involved in the nuclear Navy. They saw the ability to move from fossil fuels and doing things with all kinds of different fuels to using electricity on board ships as the primary source of power and the primary source of doing everything throughout the ship, from lighting to navigation to even drives. All right? So Mr. Blondell, he's an engineer, he's a mathematician. He comes up with a pretty simple little thing. He said, hey, if I want to measure the energy supplied by a system of N wires, let's think of a 3 or a 4 wire system, I need a certain number of watt meters, and the number is 1 less than the number of wires. So if I got a 3 wire system, I got to use 2 watt meters. Okay? That sounds pretty easy. All right? So one of the problems with that is how many watt meters are in a 2S meter? And the answer would be 1. How many wires are typically coming into the home? It's a 240 volt service with a 3 wire system. 3 minus 1 is 2. But in the 2S meter, we only got 1 watt meter, which means a 2S meter is not a Blondell compliant meter. What does that mean? That means it is not accurate at times. In fact, I would say it's not accurate most of the time now. How serious is that? We'll talk about that in just a few minutes. A 12S meter, on the other hand, very similar meter, except it's got 2 watt meters in it, which means it is a Blondell compliant meter, and it can accurately measure energy in a 3 wire system. Okay? So if the meter installation meets Blondell's theorem, under all circumstances, you're going to get accurate power and energy measurements. If it doesn't, you're only going to get an accurate measurement if certain conditions are met. All right? So let's talk about 5S. If you manufacture test equipment, you hate 5S meters because they're different from every other form. If you're a meter tech out in the field or a meter engineer setting up field installations, you'd love a 5S because you can get a 5S to meter virtually anything. But you can set them up in a wide variety of ways. So here we're going to meter a 3-phase, 3-wire delta system with 2 CTs. Okay? Fairly basic fundamental setup. All right? We got 3 wires, 2 voltage measurements with one side common to line 2, current measurements on lines 1 and 3. Does this meet Blondell's theorem? Yes, it does. We are good to go. So I just got a 5S system that I set up, and I set it up correctly, and it satisfies Blondell's theorem, which means this metering site will always give me correct energy measurements, providing that my site remains good. My meter remains good. My wires remain tight. I don't get broken wires. I don't have a lot of corrosion. This is going to give me good readings. Now I'm going to take a 5S meter. Same 5S meter. I'm going to set up a 5S socket. And this time I've got a 3-phase, 4-wire Y with 2 equal ratio CTs on here. All right, and I'm going to try and meter it. This is a setup that you may see on your service territory. It's possible. It's not all that uncommon. All right. I got 4 wires. I got 2 voltage measurements to neutral. I got current measurements on 1 and 3, but not on 2. This does not satisfy Blondell's theorem, which means give me accurate measurements, and sometimes it's not. It's not necessarily going to be far off, but I'm going to lose a few percent in my accuracy. All right? So I'm not going to torture you with the math, but it was too much fun to put it up here. So we have a couple of things. In the previous example, what are the assumptions or the perfect conditions, and what's the right answer? The right answer for the power measurement is this, and what did we actually measure is this. What the heck does that mean? I can do all the math, and I could come up with all this good stuff, but what does it really come down to? And the answer is, how big is this difference? Well, if I have a voltage difference of 117, 120, and 119, not a big voltage difference, and a power factor of 1, I lost about 1.67%. If I got a power factor that's less than that, but my voltages were a little closer together, I also still lose 1.67%. So this is with everything working correctly. In this power measurements handbook we put together, you can see that sometimes if you have a non-Blondell setup, you can get perfectly good information. Power factors of 1, slightly unbalanced voltage or current in this particular case. But when you start getting an unbalanced current and voltage, which you typically have, I don't know too many systems that have perfectly balanced in either of those, even with a power factor of 1, you can start going off. You can start going much further off. If you look down here, 2.4, 2.6, 3.4, 4.63. You can start getting very unbalanced loads, very unbalanced voltages in here, power factors that are starting to go to heck in a handbasket, and you start getting, again, even with everything working correctly, you're starting to introduce 3, 4, and 5% errors. Why is this important? Because we've got to go back, and sometimes you can go and check a site year after year after year after year and think everything is good. The site may not have been set up correctly. You may have a non-Blondell site. All of our 2S meters are non-Blondell. Is that important? When I was growing up, because I'm really old, when I was growing up, what did I have in my house? Well, we had a refrigerator. Well, that's a nice inductive load, or nice resistive load. We had maybe a TV. Okay, it was an old TV, same thing. I had incandescent lights. Our power factor at the house was probably 1. All of our neighbors, the power factor was probably 1. Now, fast forward. We have PCs at our house. We have tablets at our house. We have LEDs at our house. We plug in our cell phones at our house. Your newer appliances can change your power factor. The power factor that we have at our house is far different. It's a far cry. The electronics in our home are starting to drive our power factor further and further away from 1. And I would say that most of the power factors in our residential services, the overwhelming majority, is not 1. Is it 0.8? Is it 0.7? No, it's not that bad, but it's not 1, which means that if I have an unbalanced voltage, which I typically do, and I've got a slightly unbalanced load, which I typically do, and my power factor is not 1, the odds are that my 2S meter is no longer giving me accurate information. How far in, how off is it? Is it 0.5%, 0.25%, 1%? And the answer is yes. It could be all of those things. But you're losing a certain amount, and it's getting worse year after year after year the longer we use our 2S meters. All right. But now we're going to go back to our transformer rated sites. What do I got to check when I go out to my transformer rated site? What am I going to do? Well, I'm going to test my meter accuracy. Yep. I'm going to test it at full load, light load, and power factor. I'm going to check my CT health. What does that mean? Well, I'm going to do a burden check on it, and I'm going to do a ratio test on it. I can also do something called an admittance test. An admittance test is a very interesting test in that it's kind of like taking a picture of the meter. And in fact, a lot of utilities do take a picture of your transformer rated sites, especially the larger ones, okay? When they go out there and you're at a refinery or something like that, or one of your big users, and you open up these big boxes, you want to take a picture. Why do you want to take a picture? Because maybe I'm out there this year, but then Joe comes out the year after. Well, if he's got a picture of what I saw last year and he opens up the box and that picture looks exactly the same, he feels a little better that nobody else has been in here monkeying around. No staff electrician has been in here rewiring the things or putting a new warehouse in, and he put the service all on the C-phase. Nobody else has been in here. I feel a lot better about the site. An admittance test does the same thing. It injects a frequency in, and it measures, the answer comes out in millisiemens, and you get a number. The number in and of itself means nothing. What you do is the next year you go out and you do an admittance test, and you get a number. If the number is the same, then just like your picture, nothing changed. You didn't get additional corrosion. There's not a looser the connection didn't loosen up on you, because any of those things that occurred would have started to change your admittance test. So an admittance test is even better than a picture because it tells you if anything changed in the circuit, including things that might not be readily apparent. And then you do a site verification, which is checking everything else about it. The wires, the connections, make sure nothing is broken, make sure nothing's loose, make sure that there's no live animals in there. That's always exciting when you open up a box and there's a live animal in there. Why is this important? Well, it's important because if I got just one transformer wired backwards, okay, remember that little white dot there? It tells me which way is front. If I got a transformer wired backwards, it actually is canceling out the next transformer. If it's a perfectly balanced load, and typically they're roughly balanced, I'm actually only going to give that customer 1/3 of what he's actually using. 1/3 if I got a transformer wired backwards. If you got 3 transformers wired up perfectly, nice in a row, you'd think it would be pretty easy to see that one of them is backwards. But if you've ever been out in the field, which most of you guys probably have, when you open up some boxes, they are not laid in there very nicely. There's one transformer near the top, there's one on the left, and there's one on the right. Are they all wired up correctly? It's a little tough to see unless you follow the wires and check the white dots. All right, one broken wire to a single transformer, one broken wire. You're losing 1/3 of your bill. Now, do most wires break clean? No, they don't. A lot of people are using stranded wires. It's the most popular wire rather than the solid copper wire. Stranded wires, you start losing more and more strands in there. And even after the wire breaks, the wire is making contact, not making contact, making contact, not making contact. Do you actually lose a full 1/3 of the bill? No, you may not lose a full 1/3 of the bill, but you may lose a good part of that 1/3. Okay? Again, dual ratio transformer, if it's marked in billing as 400 to 5, but it's really an 800, it's half the bill. And if it's the other way, it's double the bill. Neither one of them is good. Neither one of them is good. We had a utility that gave a customer a $7 million check because of exactly this problem. And they went back over the years and said, oh my God, we screwed up. They sent them a check for $7 million, and what they got back was a lawsuit. And the lawsuit said, well, where's the interest on our money? And how do we know that it's right now? And how do we know that you went back far enough and weren't, because the law says you only have to go back so many years, was it going back even further than that? And if you do it the other way and you actually give them the correct bill and it's double what it was, and you don't even try and collect the money that they owed you from before, you could literally put some of those customers out of business because they can't handle, as an industrial customer, they couldn't handle double the electric bill. So it's a lose-lose. All right, what else can you see? Cross-phasing, okay? Loose or corroded connections. CT mounted backwards we talked about. A CT with a shorted turn. How does that happen? It usually does happen when you put too much through it. A magnetized CT. One of the things you do when you do a burden test is you usually demagnetize those CTs at the end. You could get a burden failure. You could get an open or a shorted secondary. You could get a mislabeled CT. Just because it says it's 400 to 5 doesn't actually mean it's 400 to 5. While all the manufacturers are good, like all of us, we all have a bad day. We all make mistakes at times. And I used to think that was, well, how often could it happen? It actually happens more often than you would believe. Ensuring all the shorting blocks have been removed. Typically, the last thing you do after you put in a new installation is you pull out all the shunts, right? You remove the shunts. And if you don't, what happens? You're not really using those CTs. You're not getting any real energy measurement at your meter. When we were first coming out with that little device that I showed in some of the pictures earlier, we were doing some testing with a local co-op, and we said, hey guys, we'll send an engineer out with you, and we want to test out our unit, and you guys will get the ability to test your transformers. And what we found was, I got to a ball field, the co-op was supplying the municipality, opened up the cabinet, and the shunts were still in. The ball field had been in there for about 6 or 7 years with all their lights and stuff, and the municipality just thought they were getting a great streetlight rate or something. You double check the meter number to make sure you've got the right meter number and the right location. You can come back with this great report showing your boss how you found all these mistakes, only to find out you were at the wrong site. That happens more often than you would think, and it happens especially when you get to a large industrial customer who has multiple metering sites. Yeah, there's 10 different meters here at this site. Were you really at number 3 or were you at number 4? Performing a visual safety, okay? You're looking for the intact ground. The enclosure is attached. How many times have you gone up and the only thing seeming to hold up the wall is the enclosure? Unwanted voltage, proper trimming, site tidiness, stuff that's gotten into the cabinet, animals or otherwise, water in the bottom of it, etc. Always assume you always walk up with your PPE on because that box could be live. There could be a short in there. Had a utility tell me the story last year at a meter school. They got a call from a customer. They'd moved out of a manufacturing site. It was an old Quonset hut, and the customer called and said, hey, we just got a bill for $30,000. The place has been empty for 3 months. We usually get a bill for, $50, $60. Something's wrong. They went out to the site. As they opened the door to the Quonset hut was live. They went in and found that somebody had been trying to take all the copper out of the building, and there was a set of wire cutters that was welded into the box, and the whole place was live and going to ground. They did not find a body, so either his friends pulled him out or he was lucky and he was thrown clear. But assume everything could be live, especially as you're walking up to a box. You're checking for energy diversion, intentional or not, broken or missing wires, jumpers, open test switches. Nothing more embarrassing than leaving an open test switch. Those plastic covers that fit on the test switch, most people don't use them anymore because they say, the test switch is inside an enclosure, I don't need it for protection. Those covers were actually designed so that you cannot leave an open test switch. The covers are designed, there's an ANSI spec to them, so that when you put that cover on and tighten it down, if you did leave a test switch open, you wouldn't be able to get it on, and if you didn't leave it fully closed, it would actually help to close that test switch. So there's actually a reason for those covers. But if you don't use the covers, you could test a site and leave that test switch open. Unconnected wires, foreign objects. Again, simple broken wire can lead to a massive metering error. We're worried about 0.5% or 1% on our meter or our transformers, and yet a broken wire loses 33%. Lightning arresters, transformer checking for proper grounding, bonding, burden testing, voltage checking. You're checking everything at that site. As soon as from the way the box is mounted, once you open it up to everything in the box, you are checking. One of the best things you can do is clean everything. You see some corrosion, clean it all. We have customers that like to buy test switches that are unplated, and their thought process is when they get to the site, they're going to spend 20 minutes cleaning them all, but they're going to make sure that they're all perfectly clean. It's possible. It's personal choice. All right, I've got a nice site verification checklist. We are going to send out this presentation to everybody, so you will get a copy of it. You can actually check the rotation of a service by actually closing in the test switch. I'm not going to go into that, but if you want, we can have some experienced guys that can show you how to do that. On occasion, you will find a bad test switch. Of course, it wouldn't be a TESCO test switch if that were the case, but on occasion you could find a bad test switch. Suspect everything. Check everything when you go out there. Check that it is a Blondell compliant. Everything may be perfect. Check and see how many watt-hour meters do we have in here? How many lines do we have? Do we have 2 for 3, or do we have 2 for 4? Okay. There's not too much loss compensation anymore, but sometimes they're out there. Again, anything you find in the box can lead to a big issue. All right? More of the same. Again, even simple things like the shunts. All right? If you see signs of excessive heat, if you see wires that clearly had overheated, could be a sign of a problem. If you see issues at the meter base, could be signs of a problem. Anytime you see melted plastic or discolored wires or anything, it's obviously related to heat. What went wrong? Okay? Why are we checking these? One of the beautiful things about AMI is that it gives us a lot more time to focus on our CNI metering, and because we don't have to spend as much time on our residential folks. And the CNI guys, it's where all the money is. Most utilities, more than 70% of their revenue comes from their transformer-rated services, even though they only represent maybe 9 to 10% of their customers. That's a typical percentage, is 9 to 10%. Doesn't mean your utility is that way, but most utilities, 9 to 10% are transformer-rated, but over 70% of their revenue comes from there. All right? If you do periodic site inspections, we recommend every year, transformer-rated. If you could, get out there every year. If you can't, you start with your biggest ones and make sure you see them every year. The next biggest ones maybe every other year. But biggest thing is stop billing errors. Again, there is no win-lose or win-win. It's a lose-lose if you have a billing error out there. Okay? All right. Okay, let's take a look here. I got a couple of questions. Patrick, are most of these items on a site verification checklist overlapping for checking high burden issues? I would think many of them could impact burden. There is an issue, and it would be a good place to start investigating. Absolutely. So when you do a burden test, you're actually checking the burden of the transformers. However, what you're not doing is checking the burden of the site. So to actually improve the burden on the site is you are taking the wires out, you're checking them for corrosion, you're cleaning them up, you're checking to make sure everything is tightened down. All right? So absolutely. All of these things overlap with the burden. Many of the issues that I listed in that checklist will add to the burden of that site, which means that you have a very strong potential. If you remembered how that chart kneed off, your accuracy goes way, way down. All right? So yes, Patrick, you're absolutely correct. They do overlap in a big way. All right? So what did we cover? We got a minute to go. I think we did cover the difference between self-contained and transformer-rated meters. We touched briefly on meter forms. We talked a little bit about test switches and CTs, a little bit of why Blondell serum is important, meter accuracy testing in the field, checking the health of your CTs and your PTs. And really when you get out there, it's about checking the site, not just meter testing. So again, why is it hard to see whether these transformers are all in the right direction? Yeah, you bet. It can be a little daunting to figure out, is this one the same? Yeah, okay, it's going this way, and then that one's going this way, and that one's going that way. Is that all the right direction? And the answer is, in this case, yes, but you got to track it and make sure it is. So the most important thing, if you get nothing else out of it, it's a site verification. It's not just meter testing. It's not just transformer testing. It's a site test. It's a site verification. So exactly 12 o'clock, and we are exactly finished. These are the upcoming presentations. We've got the next one's on safety. Then we got one on test switches, CT testing, ratio burden and admittance testing, asset inventory management, harmonics, complete site testing, electric vehicle trends, streetlights, and 5G metering and testing. So we've got a bunch of different things. If there's something that you guys would like to see as a session or added to a session, please let us know. If you liked it, let us know that. If you didn't like it, tell us why and what we can do to fix it. All right, we'll let you guys get back to your regularly scheduled lives unless there's any other questions in the chat. All right. Thank you, guys. Have an awesome day. Bye-bye.